Okay, so now let's have a look at example 5, which is very similar to example 4. It's just applying the definitions of concavity and point of inflection. So example 5 says, consider the function f of x equals 12x squared minus x cubed. Part A, work out where the function is concave up and then work out where it's concave down, and then work out the point of inflection. Alright, so I'm going to write down my function. I'm going to write y equals 12x squared minus x cubed. To work out concavity or to check concavity, we need the second derivative, because the first derivative gives us gradient. The second derivative gives us the rate of change of gradient, which is what concavity is, where the gradient's increasing or the gradients are decreasing. So we need to find the first derivative. So y dash is 24x minus 3x squared. Double derivative, or the second derivative, differentiating the first derivative, we get 24 minus 6x. Right, so for part 1, we need to find concave up. So what does concave up mean? Concave up when your second derivative is positive because your gradients are increasing. So that's when 24 minus 6x is bigger than 0. So rearranging inequalities. So remember, solving for inequalities is literally the same as solving as if you had equation equal to 0. The only difference is when you multiply or divide by a negative number, then you have to flip your inequality to the other one. So if you had this inequality, and then if you're multiplying or dividing by a negative number, you would flip it to the other side, and vice versa. Okay, so rearranging, moving the negative 6x across, that's fine. I'm not multiplying or dividing, I'm just literally adding 6x to both sides. So 24 is bigger than 6x, so dividing both sides by 6 like we do normally in algebra, 4 is bigger than x. So in other words, if flipping it around, usually you write it x is less than 4. So therefore function is concave up for the values x less than 4. So anything less than 4 for this function is a concave up part of the function. And we'll do the same for part 2. So concave down when your y dash dash, your second derivative, is negative. So I guess one way I remember it is up is a good thing. You're increasing, so it's a positive. So your second derivative should be positive. When you're down, you're sad. Again, you're negative. You don't feel happy. So your second derivative is less than 0. So solving this, so y dash dash is 24 minus 6x less than 0. Again, I'm going to add 6x to both sides, so I don't flip the inequality because I haven't multiplied or divided by a negative number. I've just added a number to both sides, and then dividing both sides by positive 6, I get that. Usually we write the x on the left-hand side, so flipping it around. So therefore, function is concave down for all x values bigger than 4. So that's what that tells us. And then now let's do B. So part B is saying, hence work out the point of inflection. So what's the definition of point of inflection? So point of inflection when your second derivative is 0 and the concavity changes on either side. Changes either side. Okay, so y dash dash equal to 0 means 24 minus 6x equals to 0. So 24 equals 6x, so x equals 4. Now we need to check concavity. So that's where we draw up a table of values. We're checking the y dash dash, not the gradient, but the rate of change of the gradient. So be careful there. Our point of interest is 4, and a little bit to the left and a little bit to the right is good enough to check. we know that at y equals 4, the y dash, when x equals 4, the y dash dash is 0. We also know that from A, that if anything is less than 4, then the concavity, the y dash dash is is up, which means it's positive. Oh dear, that's wrong. So let me do that again. There you go. So, okay. And go back. So we solved that y dash dash equals 0 and x equals 4. Checking a little bit to the left is 3.9. But from part A, we said that anything that's less than 4 in x value, it's a concave up. Concave up meaning that the y dash dash is positive. So we can fill that in saying that's positive because that's from part A. And also from part A, we found that anything bigger than 4, so 4.1 is bigger than 4, our y dash dash is going to be less than 0 because it's concave down. So that's from part A as well. So therefore, concavity has changed either side of x equals 4. And just like how the previous example, when we're looking at a point of inflection, we need the xy value for a point. We know the x value is 4, so what's the y value? So when x equals 4, your y value is 12 times 4 squared, so x squared minus x cubed, so 4 cubed. So using a calculator, that gives me 128. So we can say, therefore, point of inflection is 4,128. Obviously, again, you should check with a sketch. Desmos. Where's Desmos? Desmos. So y equals 12 x squared minus x to the power of 3. Okay, so initially you're thinking, oh, there's just one turning point. Where's my concavity change? Where's my point of inflection? Well, zoom out. Don't forget, zoom out. It might be a little bit trickier on your graphics calculator to zoom out, but hey, if you zoom out enough, there we go. So I wonder if I can change the x from -20 to 20. There we go. So you'll see here that I wonder if I can, no, you probably can't see it unless okay. So here at 0, 0, we've got a happy face turning point, whereas at 8, 256, we've got a sad face turning point. So where the happy face, that's the concave up, whereas the concave down is the sad face. At x equals 4, so I can't point to it because I don't have the laser pointer, but at x equals 4, which is about here-ish, there, right, you can see that's where the happy face changes to a sad face, and that's our point of inflection. So anything to the left of this point of inflection, anything left less than 4 would be a concave up, because that's part of our smiley face. Our gradients are increasing, whereas anything to the right of 4, so that's our sad face, that's our concave down, our gradient is decreasing in